purpose of the specific gravity lab is to find the unit weight of solid particles. This is an important design value, for it gives us an idea of how much the soil will weigh. With this weight, we can calculate how much weight the overbearing or overburdened soil will bear on the soil beneath. This allows us to design foundations, retaining walls, slopes, and other subterranean structures. Numerically, the specific gravity is the density of soil solids divided by the density of water. If the specific gravity is found, Gs, then the unit weight of solids, gamma s, is simply Gs times the density of water. A variety of tools are used for the specific gravity test. The most important tool is the water picometer. The standard allows one to use a 250 milliliter water picometer or a 500 milliliter picometer. We will also need a scale, drying oven capable of 110 degrees Celsius, a thermometer capable of measuring to the nearest tenth of a degree Celsius, a hot plate or Bunsen burner. We will be using a hot plate during the test. An insulated container is required, a funnel, pan, and number 4 sieve. Calibration of the picometer is a two-step process. The first step is to calibrate the mass of the empty, dry picometer. To do this, we must make sure the picometer is clean, empty, and dry. Determine the mass of the picometer and record. The scale must be accurate to 1/100th of a gram. Repeat the weighing process, totaling to 5 separate times. Record all 5 measurements. With the 5 measurements, calculate the average, also known as the mean. Calculate the standard deviation of the dataset. The standard allows a standard deviation of 0.02 grams and below. If this requirement is not met, the calibration should be repeated. In our case, the average weight of the empty dry picometer was 103.4914 grams. The standard deviation of the 5 measurements came out to 0.02 grams. Thus, our picometer was appropriate for use. The second stage of the picometer calibration entails calibrating the volume of the picometer. First, fill the picometer with de-aired water to either above or below the calibration mark. Place the full picometer in an insulated container and allow at least 3 hours for thermal equilibrium to occur. Place more de-aired water and a thermometer in the insulated container. The equilibrium temperature should be within 4 degrees Celsius of room temperature and also between 15 degrees Celsius and 30 degrees Celsius. After at least 3 hours, remove the picometer from the insulated container, being sure to handle the picometer by the top. Adjust the water level to the calibration mark so that the bottom of the meniscus is at the calibration mark. Be sure and use water that was stored in the insulated container to reduce temperature changes. Use a pipette or eyedropper to add water. Use a pipette or paper towel to remove water. Once the water line is exactly at the calibration mark, weigh the full picometer. Be sure and record the mass to the nearest 1/100th of a gram. Also take a temperature reading to the nearest 0.1 degrees Celsius. With the thermometer from inside the insulated container. Readjust the water level up or down for the next calibration. Place the full picometer, thermometer, and extra water inside the insulated container and allow for another 3 hours to pass. Thermal equilibrium will again be met. Repeat the process 4 more times for a total of 5 volume measurements. With each of the 5 mass measurements, calculate the exact volume of the picometer using this equation in the middle of the page. The volume of the picometer is equal to m sub p w, c minus mp over rho w, c. M sub p w, c is equal to the mass of the picometer and water at the calibration temperature. This is what we pulled out of the insulated container and weighed. MP is the average mass of the dry picometer at calibration. This was completed in the first step of the calibration. Rho w, c is the mass density of water at the calibration temperature. This is found from Table 2 of the ASTM standard. Next, average the 5 volume measurements and compute the standard deviation. The ASTM standard requires a standard deviation of 0.05 millimeters or less to ensure accuracy. If a standard deviation of 0.05 millimeters is not met, the process must be repeated. In our case, measurements 1, 2, 4, and 5 were equivalent. The full volume calculations are shown here. The 5 computed volumes were averaged for a volume of 249.732 milliliters. The standard deviation of the data set is computed to be 0.05 milliliters. Thus, the volume calibration is complete. The calibration of the picometer phase is now over. There are 2 methods in obtaining the specific gravity of soil solids specified in the ASTM standard. One method specifies moist specimens, while the other specifies oven-dry specimens. We will primarily focus on the oven-dry method, although there is little difference between the two. This test is relative to soil solids that pass the number 4 sieve. For finding the specific gravity of solids that are retained on the number 4 sieve, please refer to ASTM C127. Remove the oven-dry specimen from the oven. Table 1 of the standard designates recommended masses for test specimens, depending upon soil type and which picometer we are using. In our case, our soil is primarily clay, and the picometer we are using is 250 milliliters. Therefore, a 35-gram sample is recommended. 35 grams is weighed in a separate bowl or dish. To make the slurry, first break up any clods of soil using a mortar and pestle. Place the funnel in the picometer. Ensure that the funnel extends down past the calibration mark. Spoon or slowly pour the specimen into the funnel. Wash the funnel with a squirt bottle. Be sure to wash all of the soil into the picometer. Add water until the level is 1/3 to 1/2 the way up the main body of the picometer. Agitate the water until the slurry is formed. Rinse any soil sticking to the inside of the picometer back into the slurry. Agitate until water becomes a uniform and consistent color. The most common de-airing method is boiling. Other methods include vacuums. When using the boiling method, use a hot plate or a Bunsen burner to apply indirect heat. Heat slurry until it comes to a full boil. Agitate the slurry and keep particles off the inner main body of the picometer. We agitate the slurry to keep it consistent and apply the same amount of heat to all particles. Do not allow slurry to dry within the picometer. Allow the slurry to just achieve its boiling point for a duration of 2 hours. Continually agitate during the 2-hour duration. Essentially, all the voids are being removed from the soil slurry at this time. Fill the picometer with de-aered water to just below the calibration mark. In doing so, use a flexible tube or pipette. Be sure and insert the tip of the pipette or tube into the slurry as water is added. This prevents any soil slurry from splashing up above the calibration mark. Move the tip up as the water level rises. Increase the flow rate slowly as the water level rises. Again, fill to just below the calibration mark. Put the picometer in an insulated container with extra de-aered water, a thermometer, a pipette, or an eyedropper. Allow thermal equilibrium to occur overnight. Move the insulated container near the scale if it is not already there. Open the container and remove the picometer, handling only the rim to maintain equilibrium. Adjust the water level up to the calibration mark, using the same tip insertion method as described. Use the de-aered water from the container. Adjust the water level so that the bottom of the meniscus is at the mark. If water is to be removed, use a paper towel. Be sure that the inner portion of the flask above the calibration mark is dry, as well as the outside. Weigh the picometer and the slurry with the same scale used for calibration. Record the mass to the nearest 1/100th of a gram. Also record the temperature. The temperature is known as the test temperature and is very important in the determination. Once this has been done, transfer the soil slurry into a pan using a squirt bottle. Remove all remnants and particles. The pan and slurry will be oven dried to obtain a mass of dry solids. After the particles have been removed from the picometer, place the pan with the slurry and extra water in an oven and allow for drying at 110 degrees Celsius. Remove the pan from the oven. Once the soil is dry, place something over the pan to prevent external moisture from being absorbed by the sample. Allow the sample to fully cool. Remove the top, weigh and record the mass. Either transfer or subtract the weight of the pan so that only the weight of the dry solids is recorded. The first equation in the calculations portion of the data reduction is the mass of the picometer and water at the test temperature. Add the average calibrated mass of the dry picometer to the average calibrated volume of the picometer times the density of water at the test temperature. Remember that the test temperature was the final temperature measurement of the soil slurry after sitting overnight. Our test temperature was 22.8 degrees Celsius. After referring to Table 2, the density of water at that temperature is found to be 0.99759 grams per milliliter. Using our calibrated dry mass and calibrated volume, MP and VP, the mass of the picometer and water at the test temperature is calculated to be 352.6215 grams. The mass of the picometer and water at the test temperature will be used in the next equation. Use the following equation to calculate the specific gravity of solids at the test temperature. Divide the mass of the oven-dry solids by the mass of the picometer and water at the test temperature minus the difference between the mass of the picometer, water, and soil solids at the test temperature and the mass of oven-dry solids. This result will yield the specific gravity of soil solids. After drying the solids, the weight of the soil solids came to 34.83 grams. Implementing the rest of the mass measurements, a specific gravity of 2.69 is tabulated. This is typical of a clay soil. Most soils will yield specific gravities in the 2.6 to 2.8 range. Therefore, our results are consistent. This concludes the specific gravity by water picometer test procedures and data reduction.